non-zero value for the previously fixed mode. So the bulk field goes as Z to the G minus delta, which is just right. When delta is less than D, this grows as we move away from the boundary towards lower energy, exactly like, of course, the corresponding operator. And then we got to figure out what happens when the perturbation becomes large, at large Z, low energy, things become nonlinear, and then we have to figure out what happens next. And it's actually, within N equals 4 theory, there's a nice example, a rich example, that I'll describe, which is to add the superpotential masses for 1, 2, or 3 of those N equals 1 superfields. So 1, 2, or 3 non-zero. And this is going to have to be fairly descriptive, and this section of the written notes will be heavy on references. This is more a guide to what people have done than all the details. But I'll tell you what, for example, one non-zero mass, it's believed to slow to a new fixed point. A new strongly interacting fixed point. For two masses, it's believed to flow. For two masses, what's left, the massless part, is just the N equals 2 gauge theory, which is just the subject of Seiberg-Witten. It's believed to flow to an SUN version of Seiberg-Witten, which in particular means that the massless sector is a U1, is non-interacting. That the massless sector is a just a U1 subgroup of the original boundary symmetry, which means it's non-interacting. With three masses, the massless sector, the chiral superfields are all massed out. What's left is the N equals 1 gauge field, and that's believed to be a confining theory, and so with three masses it should confine. That's expectations from various kinds of field theory reasoning, and it's interesting to see the way the geometry reflects all of these. Well, that's within that's a central point within that space. Oh, I'm sorry, you're right. I'm sorry. Actually, I forgot that. Let me come back to that. That's a really good point. So let's see the way that the geometry reflects all of these. So now the point of view, I mentioned for a while back what the dictionary was of these operators. They correspond to the free-form fluxes on the 5-sphere, and the 5-sphere has no free cycle, so these are not, typological, not monopole, just kind of, dipole free-form fluxes. And the supergravity folks have a trick for studying these called consistent truncation, where they write down an effective 5-dimensional theory with this mode, and then solve it. And it's really magic, because there's no symmetry that would prevent this. There are the particular mode here, some harmonic on the sphere, it's not lower in energy. It doesn't keep predicting with them, but there's some supergravity magic where they can write down 5-dimensional Lagrangian, solve it, and then just a 10-dimensional solution, and it can be applied to this case. And so first, for the case of one mass of flavor, when they do it, they get a 5-dimensional potential that looks like something like this, where the N equals 5, so this is the potential for this mode. The N equals 4 theory that we've been dealing with lives up here, which seems kind of unnerving, but as we discussed, this mode has a negative mass squared, but if it's not too negative, then the boundary conditions stabilize the system a la Brightfloater treatment, and it's okay to have this right. We know we're in this situation because if you go back to the the M squared equals delta minus D dictionary, being relevant, that is delta less than D, exactly means being tachyonic in the supergravity, and you kind of guess what happens. There's some solution where the field rolls, so here's the value at the boundary, here's the value at the horizon, and there's some solution which has, here's Z equals 0, here's Z equals infinity, here's ADS region. There's some transition region as you roll down the potential, and then there's a new ADS solution. So this is a particular, this is exactly what the field theory reasoning leads one to believe, that you flow from one strong coupling theory to a new strong coupling theory. You can match up the details of what you accept. Yes, sir.
Say stability is equal to stability is equal to
this is instability? The near ground is satisfied here, meaning that there's no instability. Tom talked about this too. There is no instability in time, but there's in some sense, but it's not really instability. But you don't roll down the thing in time because the gradient energy protects you. But you can roll down it when you travel in space in the radial direction. That's what you're doing. Sorry.
I don't understand what the instability is.
If you see a potential like this, you don't expect this to be stable. It's a solution. That's all I'm saying. And I'm saying that it is stable. I'm not sure if I get the question, but I'm saying it's a potential stable because there's also gradient. There's also gradient energy that if you look at time evolution, actually, turns the potential up. Sure. In dual gravity theory, you have this is the potential in the gravity theory. Sorry, this is the potential in the gravity theory, and when you look at the radial equations, there are solutions which start here and end up here. Now, with two masses, you can do the same thing, and there's some other direction in the potential that you're flowing in, and this one's different because you end up flowing sort of out to infinity in field space. With two masses, the same strategy, when you lift it to a 10-dimensional solution, gives you a singular solution. So this is with one mass. It does what you expect. Two masses gives you a singular ND solution. But it doesn't have a band singularity because then you look at it carefully and you realize that it's just a bunch of D3 branes. And so what the geometry is here is that, well, let me draw ADS space, Planck ADS space, this way, and this is Z equals 0 the boundary, and the spatial things are shrinking up, and it never gets to Z equals 0. It kind of for the picture. But the point is that the whole space, I should really draw it. The point is that you never get to Z equals infinity. The geometry smoothly rounds off. This is actually how the ADS, the compact direction is here. And this is Z equals 0, and they smoothly round off at some T equals Z max. In terms of the metric, you have this ds squared is L squared over T squared, eta mu, dx dx. And again, in the ADS geometry, one has arbitrary low energy excitations by moving the excitation to smaller and smaller z. That reduces its energy in terms of the gauge theory as much as you want. But once you cap off the geometry, you can't do that. They pushed on the problem, made some progress, but I don't think they ever gave a general solution. It's not smooth when the fields run up to infinity. Well, it's unique that it's in a recipe. They look at the theoretical equation, and it's a trick. And it's a trick which it certainly is one-to-one in the way it's used now. Well, in fact, let me come to it. When you get three masses, this becomes even starker because let me see what happens to three masses. With three masses, you can do the same thing. The five-dimensional thing flows off. You get a singular 10-dimensional solution, but it's not any recognizable sensible brane. No, this is going to be, so there's no 11 D left. Yeah, well, I mean, again, this is a singularity, so that's a degree range. Let me finish this, tell you what happens with three masses. So with three masses, if you're mass transfer, you look at the gauge theory side of the duality for inspiration. If your superpotential is W, then alpha equals, say, pi alpha squared, plus, you got some alpha beta gamma, commutator of pi alpha, pi beta, pi gamma filtration. And I'm leaving off the constants. Then the F-turn equations tell you that, again, I'm leaving off the constants, gamma phi alpha is epsilon alpha beta gamma, commutator of phi beta, phi gamma, which is to say that you have vacua, for any, so again, these are n by n matrices, and you have vacua for, so there is one vacuum for each n-dimensional representation of SU2, then it doesn't have to be reducible. So there's a huge number of vacua, including the trivial one, phi equals 0, and phi equals 0 actually is the confining one, and the other ones have various sort of mixed confining Coulomb behavior. Remember that the scalar parts of these superfields arose as the coordinates of the D3 branes, and this is saying that those coordinates are becoming non-commutative, which comes back to the question from the last lecture, because Rob Myers explains that when you put D3 branes in a transverse flux, it becomes energetically favorable for the coordinates to become non-commuting, and they pop out in two directions to become D5s. And so the correct behavior of the supergravity with three masses is that it ends on, it actually ends on a D5 or an S5, or in fact, sums of many 5 branes. And the fact that there are many ways to cap off the geometry reflects the fact that the theory has many vacua. And so there's a nice match between, you see Elizabeth settling versus a nice match between theoretic prediction and what the brain tells you, but also it takes some trial and error in many cases to figure out where the geometry flows. It's not always obvious. The perturbation gets big, and it's not obvious what the geometry that does it, and in particular it's useful to have insights of the gauge theory as well. By the way, you can, once one does this, one can go back and figure out what the consistent truncation was doing, and it was trying its best. It was producing some smeared version of the D5 brane. It was steering the 5-dimensional object out into like a 6 or 7-dimensional object. And so it was trying very hard to give the right answer. Okay. Now, the last thing I want to say about, I'm pretty much done. The last thing I want to say about this is, I told you that one of these theories confines, and I want to tell you how to see that. So, one observer I talk about is to measure the potential between a source of a quark and an anti-quark source fundamental. That maps so the QQR potential. Fundamental. There are fundamental. You can always get fundamental sources. So here is your boundary, and it corresponds. So the string, if you think about it, in going back to Tufts and Wilson, is thought to be the color electric flux tube. And one could say more to justify this, but time is short. The way you calculate potential is to consider a string hanging down to the boundary, and then subject to suitable renormalizations. The potential is just the tension of that string. Again, the potential is the total energy of that string coming from its tension. Now, the tension, the effective tension, so again, this is the z direction, is the local tension times the translation, the gravitational redshift, the translation from local inertial coordinates to the global coordinates. And so the further it hangs down, the less its energy, the further z it hangs. And in fact, in an ADS phase, you get, as you must get, because just by the scale invariant mismatching units, as you pull the ends further apart, the string hangs down lower, and so it can reduce its energy in such a way that the potential goes lower as much by symmetry. So of course this is interesting, but no time for that. In a confining vacuum, on the other hand, we have encountered this idea that there's some Z-max. And so, the draw is a bit larger. The string hangs down, but it can only hang down as far as the space lets it, and then you pull the ends further and further apart, and most of the string is just running along the bottom of the space at the largest value of Z, the most infrared value of Z you can get. And so the effective tau of the string is just epsilon 0. It confines. And that's what happens with three masses. With two masses, the southern nebula are not confining, they're Coulombic, but for a different reason than over here. There is a floor to the space, as I was saying, for n equals 2, for the two masses, but there's also the duplicity free branes. And so now I'm going to draw the same picture. So here's Z equals 0, where the string hangs down from. Here's the floor, and now I'm looking from a different perspective so I can see, those D3 branes. So I'm looking now from a perspective that sees the three directions more explicitly, and so here's your D3 branes sitting at the bottom of the space, and the strings hang down. But once the string ends on the D3 brane, it stores its flux. But the flux is just a U1 gauge field, and it's free to spread within the D3 brane. So you get a Coulomb potential for a different reason than you did in the AES space, but it's still Coulomb. That's the general thing with D3, particularly with a lower dimensional object dissolves in a higher dimensional, ends on a higher dimensional. It doesn't just end. There's always some, the arrows running the other way, I guess. There's always some flux carried by these objects, which has to somehow run through the higher dimensional object. But again, because the three branes have a really gauge field, the flux can spread freely. Okay, so that's the general idea of our G-flows and also some specifics. Yes, sir. You've got strings, you have D strings, and you have DQ bound states. So yeah, you have the entire sort of SL2Z multiple objects. So in fact, with all of these phases, you also want to ask about the tough blue, the status of the magnetic, essentially magnetic objects. Are they? And similarly, you can ask it for external bionic sources. Some CFTs have operators in the range between the minimum allowed by sort of unitarity, by the Coulomb algebra, and half the dimension of the space of the CFT. And this is the regime where, as we said, you have to take the alternate boundary condition, the less obvious one, on the scalar field at Z equals 0. But this is also special for another reason. It's special because 2 delta is less than Z. And so the double trace term operator squaring the original operator is relevant. Now, again, I'm using here large N factorization. In the large N limit, the amplitudes for the two, because some two operators at a point that are each connected to the rest of the graph, but the reading in N amplitudes are fully disconnected between the two